Hello guys, welcome to today's class where we'll be looking at another example on operational tables, that is operational tables on binary operations. So we'll be trying to combine our closure property, our commutativity, identity elements, and the inverse elements, which are only operations we can perform on two variables of binary operations, that is like the commutativity, unlike the associativity and distributivity, because those ones have more than two variables. But in this case, we are dealing with just two variables, hence the reason why we use our horizontal axis and vertical axis for our tables. So we'll be considering how we can actually relate these two for our identity element, inverse element, commutativity, and closure property. Now, looking at this question, we have a question here that says, consider a set P equals to A, B, D, and E, and the binary operation asterisk defined by the table below. We have a table here, and then we are asked, we are already given a table, a complete table here, and we are asked that from the table, write down the value of Roman figure 1, A operation E, Roman figure 2, D operation A, Roman figure 3, E operation B. Now, the very first thing we need to do, in fact, the tabular presentation of our binary operations is one of the easiest way we can actually have the binary operation. Why? Because it is very easy to map out and easily pick out. Now, if you look at this one, the very first question here, we're given a set P equals to ABDE. So for our solution, we bring out the set we're given, a set P containing ABDE, and then we're told to find the value of A operation E. From the table here, we can easily decipher the value of A operation E. We can take this axis as our reference axis, that is as the first axis. This one will be the first variable side, and then this will be the second variable side. Why? Because we can take it, okay, you want to take A here. A on the first, operation E on the second. We take A on the first, and then E on the second. And then we look at where they intersect. This one goes towards the right, and then they intersect at this point, and then this becomes our value of A operation E. So I can say for my A, my figure 1 here, my A operation E will give me E from the table. For my figure 2, I was also asked to find D operation A and then on my figure 3, that's an E operation B. So from the table, looking at D operation A, that is D on the first and A on the second, D on the first, this is D here, and then A on the second. Where they intersect at D. So our value here will be D, so our answer here is D. Go to the next one, we have E operation B. Looking at E here, operation B, we have B on the second axis. Where they intersect at the point D, which is what will be our value now. That means the value of our operation here is the D. So we are done with A. We are going to B now. For the B part, the B section of this question, we were told to determine if the set ABDE is closed under the operation asterisk. We were told to determine if the set ABDE is closed under the operation asterisk. To determine if it is closed, we need to consider all the elements that are inside the diagram and decide if all of them are members of the set, if all of them are elements of the original set. And if you look at the elements in this table, you see we have A, B, D, E. Everything here is between A, B, D, and E. Now because everything here contains A, B, D, or E, then since A, B, D, and E are all elements of the set P, then the operation asterisk is closed in that P. Because all of the elements that are of P, they are inside the table, and then there is not one element inside the operational table that is not in the set P. So we can say that was the operation is closed under the set, under this operation. Yes, the set is closed under this operation. We have section C. We ask, is this operation commutative? Now, to determine commutativity from the table is a very easy process. First of all, we need to be able to identify the formula that we use to express commutativity. For commutativity, recall that for commutativity, when we consider a particular A operation B, it should give us B operation A. That is, for everything that will be happening here, it should be giving us reverse of each other. That is, if I have A operation B, even if it is A operation D, it should also give me D operation A. If it is A operation E, it should also give me E operation E A, and so on and so forth. And like the B operation D now, B operation D should also give me D operation B rather, to show that what it is commutative. Another one that we should have, B operation E will give me E. And then the last one we should also have is the D operation E should also give me E. And then if you look at it from the table, you can consider all this. From the table, we realize that what our A operation B is B, our A operation B is B, and also look at B operation A is E. Now, A operation B, from the table, A operation B is B, while B operation A operation B is B, while B operation A is E. Now, A operation B is B, and B operation A is E, meaning they are not equal. Let's consider another one. We have A operation D and D operation AD and DA. If you look at A operation D here gives us D, or D operation A also gives us D. This one are the same, that is, they both have the same value of D. These ones are equal. Okay? Let's look at the next one. We have A operation E and E operation A. A operation E and E operation A. A operation E here gives us A, and E operation A gives us D. So this gives us A, and this gives us B. So meaning that what they are unequal. You look at the next one. We have B operation D and D operation B. BD and DB. For B operation D, we have B, while D operation B gives me E. So this gives me D, while this gives me D, meaning they are unequal. You look at the next one. B operation E and E operation B. B operation E giving us D, and E operation B giving us D also. So in this case, we are having both of them to be D. I mean, both of them are equal in this case. If they are equal, you can see both of them give us D. I mean, they are equal. We look at the last one. We have DE, D operation E, and E operation D. D operation E here gives us D, and E operation D gives us E. I mean, we have a value. This one gives us D, or this one gives us D. E rather. So if you look at it, you realize that what the two values here are unequal, and that inequality explains that what this is not commutative. Now, you might realize that some out of the six relations we have here, we realize that what two of them are equal. Two of them show commutativity. But because everything is not showing commutativity, once there is one relation that is not showing its commutativity, then the whole set is not commutative. So I just need to say that what the operation is not commutative. So this is what we call it today in this class. In the next class, we'll be looking at how we can actually determine the identity elements and the inverse elements of this same question. See you next class.